Welcome back. For the next video or so, we will look at the reactions of alcohol. So they can be split into multiple different reactions. We can undergo dehydrations, oxidations, substitutions, reductions, esterifications, tosylations, ether formations, all sorts of various things that can happen. So first, what is an oxidation? Oxidation typically is adding of oxygen or O2 to this, or say a halogen, or we could look at it as the removal of hydrogen or H2. The reduction will be just the opposite, the adding of a hydrogen, the loss of an oxygen or O2, or the loss of halogens. So, but it's not simply the addition of a proton or a hydroxide, not just simply the adding of water or the adding of HX. But so generic terminology, we're going to use the generic terminology if we want to say oxidation and we don't really want to specify what the reaction is. We're going to just put O in brackets. Oxidation of the bottom is going to OH. If we wanted to reduce it, we would put H in brackets. So that's a generic look at this. But these have various different effects, starting with from an alkane. A primary alkane can obviously go to a primary alcohol, which then can go to a which can then further be oxidized to a aldehyde, and further be oxidized to acid. A secondary alkane, it's a reactive group, can go to a secondary alcohol and can further go to a ketone. But it stops there. A tertiary alkane can only go to a tertiary alcohol, and it stops there. So depending on what type of group we're oxidizing, reducing, that determines where we can end up. I mean, essentially, if you look at it, a primary alkane has 3 hydrogens attached to it. And so it can undergo 3 steps of oxidation. A secondary alkane would only have 2 hydrogens and can only undergo 2 steps of oxidation. A tertiary would only have 1 hydrogen and thus only 1 step of oxidation. Now we're going to look at a bunch of different oxidizers, and they have certain conditions, but all these can be pretty much used. Common oxidizers include hypochlorite, so sodium hypochlorite. You might see some sort of chromium. You can see some sort of version of some chloride, some iodide, or iodine, sulfur, some sort of manganese. But they all have a very similar mechanism using acetic acid as a catalyst. So let's just look at hypochlorite. Hypochlorite, which is so we have our acetic acid. Lone pair goes and attacks and removes the acid. Form hypochlorous acid. Put in lone pairs. Hypochlorous acid. Now this hypochlorous acid can undergo this step. This first step is really easy to do. Second step is a little bit harder to do, but under the presence of enough acetic acid, we can depronate another one to form our form this compound. So not super stable, but now suddenly we have a very reactive intermediate. We have a chlorine as a good leaving group. A good leaving group. A positive chlorine that wants to, as you'll see, donate electrons. So in the presence of okay, so let's look at a okay. So we can add a secondary alcohol here. So secondary alcohol, how is this going to be oxidized to a ketone? So it's going to react with our structure here. So we have attacking the chlorine leaving for some water. And now we have a strange little compound here, chlorine H plus. The presence of water or the acetate that we had earlier, that will depronate this guy. Much easier to depronate this guy than to kick the chlorine back off. And so now we have a hypochlorous group on top of, attached to the carbon. This hypochlorous group, in the presence of the acetate, can undergo one more step. So the acetate that we conveniently made, the first step, will depronate this guy, causing this lone pair to swing over to the oxygen, allowing this to kick off the chlorine. So the final step now has us reforming our acetate and forming chloride. So this hypochlorous is turned into chloride, all said and done. The hydronium that we formed in this step, essentially, if that was acetate, essentially we could we regenerate the acetic acid as the catalyst on both steps. And so hypochlorous goes to chloride as we oxidize this. But that is the quick mechanism for the oxidation. Now, look at chromic acid. Chromic acid is another one we could use. It's more toxic than sodium hypochlorite, but it's also a lot more reactive. So, chromic acid, we use our sodium dichromate, and when it's put in water and sulfuric acid, it forms our chromic acid. And you form the structure of chromic acid is essentially similar to the structure of H2SO4. OH, OH. And we have two equivalents of sodium bisulfate as a byproduct. So this structure right here is our chromic acid. It's a reactive structure. So what does this do? And when we mix, though another way to represent this guy is often just, we could say CrO3 is another way. So we can do chromate, H2CrO4, or Cr2O7 minus. All of them do essentially the same thing. So what happens? So we have, just looking at a similar reaction, secondary alcohol, oxidation of a secondary alcohol. I'm leaving off the reactive hydrogen for now, but so we have HOCr bond OH. The first thing that occurs is a dehydration. This is two steps, but you attack, you move the proton, form water, and then when water leaves, you swing up, and basically two steps, we form a bond between the chromium, what was the chromic acid, and my alkane. Then from there, this hydrogen here becomes incredibly acidic because of the it's very positive, while in this we have all this electron density pulling this way, and so water can then attack here. Lone pair swings up, and that swings back over. So the byproduct there, when that attacks, it kicks that off. We have our ketone again, and you have essentially this structure. OH. Okay. Now the exact nature of this is not super important. Just know that we start with an orange chromic acid, and by the end we get a blue-green bluish greenish byproduct. So it's a good way to test for this. There's actually a chromic acid test that will test for oxidizable alcohols. So if you mix in chromate in with an alcohol, you'll turn from orange to blue-green, and you can say, oh, yeah, I had alcohol in there. At least the alcohol that can oxidize. Now, please note, in chromic acid, primary alcohols will go all the way to acids, all the way to like a carboxylic acid, because chromium is much more reactive than some of the other things. So sometimes you want to stop part way. So there's something called tempo, T-E-M-P-O. It's essentially a stable radical that is used with sodium hypochlorite to temper this reaction. The structure is not super important that you know it, but draw it. It's a stable radical that when used with it tempers the oxidation. Tempo tempers the oxidation. So basic idea, if I do this, I have a primary alcohol and I use sodium hypochlorite and tempo. The byproduct is not an acid. I can easily stop at an aldehyde. However, excess sodium hypochlorite with tempo will still fully oxidize. So you obviously have to have one equivalent of sodium hypochlorite. It basically slows this down to a point where you can extract this. You don't get the full oxidation because you can slow it down with the tempo. You can make it a little bit slower, but however, why would you want to do that? You get very good yield. You don't have to worry about byproducts, not nearly as toxic. You get a lot of the product you want. There's another one you can use that's weak. So you can classify these oxidations into weak and strong, which is PCC. Another weak, let's say another mild oxidant. It's a little bit harder to make, but it's a good one. Okay, so what is this? PCC is essentially we're modifying our chromium. It's like it's pyridinium, I do believe, chromium chloride. So this pyridinium and the chloride essentially is a way to turn a primary alcohol to an aldehyde. So there's various ways to do this. But you want to be very careful when it talks about oxidation. You want to classify this. Do we have a strong oxidant or a weak oxidant? Do we have a lot of the oxidation to the material, or do we have little? Because aldehydes are particularly reactive. So if it's a strong, it's going to keep going. If it's a weak one, maybe stop it at an aldehyde. But let's say there's other strong oxidizers such as nitric acid and permanganate, but we've already kind of seen them. See, there's also, let's see, yeah, I'm not going to go over that. There is the natural oxidizer of nicotinamide adenine dinucleotide, the NAD, that occurs in the body, but you'll go over that more when you get to biochemistry. But that essentially turns an alcohol into an aldehyde and NADH. And then they can follow by aldehyde dehydrogenase. That's gonna turn that to carboxylic acid to make more NADH. So, so a few other reactions. Alcohols as a nucleophile and electrophile. Alcohol will act by itself, acts as a weak nucleophile. But when the OH bond is cleaved, it becomes a strong nucleophile. However, if we can cleave, so from here, see, if I can go to R3, see, O minus is a weak nucleophile, strong nucleophile. However, if we can cleave the CO bond, we can get a particularly strong electrophile. So depending on how we go about this. If we cleave this by protonation, so we protonate this, add water, add hydrogen, and lose the OH. But if we use base, so depending on what you do. However, protonated alcohols are very acidic. So how do you lose this? How do you lose this? Well, we can lose this by making alcohol into a really good leaving group, which is with a tosyl. What is a tosyl? A tosyl group is essentially a toluene, like sulfonyl. Toluene sulfonic acid is a pretty strong organic acid that you can use. And the best part is when you snap these things together, you make a really good leaving group because this is particularly stabilized. Not only is the sulfur really good resonance by itself, but then with the added toluene group adding into the resonance, further can stabilize any negative charge we may put on. So a common thing with this tosyl is we're going to do, say, ROH, presence of TSOH, our tosyl group, in benzene, in pyridine. We're going to form a tosyl alkane in water. Or alternatively, we can also, instead of a tosyl acid, we could have a tosyl chloride in the same settings. And we'll still produce a tosyl group. And instead of water, you'd have HCl as a byproduct. So now we have something, a good leaving group that we can easily kick off. So we're going to finish off this video real quickly by looking at two quick reductions of alcohols. How can we reduce our alcohol? We're looking at, in this case, a cyclopentanol. We can first do this in two steps. One way is, first is dehydration and elimination. / elimination. Which is, we can just do that with sulfuric acid, strong acid, and heat. We protonate there, and then in the presence of heat, we kick off water and form alkene. Then step 2, hydrogenation. Step 2, we add hydrogen and our platinum, and we can fully reduce this down. But another way, with tosylation and then hydride addition. So same product, we add tosyl chloride, form our tosyl group. And then we can then add tosylation. And then we can add lithium aluminum hydride addition. Lithium aluminum hydride, and that just kicks that off. Don't have to worry about some rearrangement, don't have to worry about stereochemistry. That often, so that's where we'll stop for now. I will continue where we left off and